Okay, so I want to do a video to go over the Chapter 12 review, but like on the other hypothesis test reviews, I didn't want to have to rewrite all the tests again. So just like those other hypothesis testing chapters, I'm doing a review where we're kind of looking at the key. I'm just going to walk y'all through it. So number one, a town manager is interested in comparing requests for various town provided services, such as street maintenance and garbage pickup, with nationally published proportions of requests for the same services. Each request in a random sample of 500 service requests from the town was classified into one of 10 different categories. Which of the following tests could be used to determine whether the proportions of service for the town differ from national proportions? Since we're dealing with categories, that should instantly tell you it's a chi-squared test. As soon as you say they're broken down, as soon as you see that they're broken down into categories, that should instantly tell you, oh, chi-squared. And so to that extent, if we look at our answer choices, we're already down to a 50-50 shot. A is gone because A is a t-test. B is gone. B is a t-test. E is gone because E is a t-test. So that leaves you with C and D. So then we have to think, okay, association means the same as independence. Are they wanting to see if two populations are independent? No. So that's what throws that one out. This is a goodness of fit test. They're wanting to see, does the data fit the national data? And it's a one-way table. So yeah, goodness of fit deals with one-way tables. So the answer is D. Number two, a group of men and women were surveyed to investigate the association between gender and the number of friends the person has on social media. The results are shown in the table below. Notice this is a two-way table. We have men and women, and then the number of friends broken down into categories. So two-way table here, which means being that they're categories, that leaves us to, for one, we've got to look at chi-squared. It's categorical when you look at chi-squared. So we could even stop there, jump down to our answer choices, and throw out A, B, and C. We're not doing a t-test. We're doing a chi-squared test. Which of the following procedures is the most appropriate for investigating whether an association exists between gender and the number of friends? Association means independence. So we're doing a chi-squared test for independence. Answer is E for number two. Okay, number three. Some people believe that criminals who plead guilty will on average get lighter sentences. The following table summarizes that for a random sample of San Francisco defendants in burglary cases. If the null hypothesis is that the plea and sentencing fate are independent, perform the calculation to find the expected number of individuals who plead guilty and are sent to prison. Notice here, this is just asking for expected count for plead guilty and sent to prison. We're just wanting the expected count of the cell that has 392 in it. That's all we have to find. So we do the row total times the column total divided by grand total. It's going to be 450 times 956 divided by 1028. And that'll get you approximately 418.48. That's all they're asking us to find. We don't have to do a test. We're just asking to find the expected number. That's it. You know, or a question like this could come in on the AP test, is this could easily be a free response, and then this may be like part A. In other words, do you know how to calculate expected count? Then part B may be to do the actual test. Show me you know how to get the expected count. And then part B, we don't have that on here, but that could happen. This would be a really good part A question. Okay. Next one, we have our first full-blown hypothesis test. I'm not going to read the whole problem. If you've done the review, chances are you've already read it. They want us to test the hypothesis that the transplant outcome and what we're calling the experience level of the population of troublesome bears are independent, which means we're testing for independence here. So for the purpose of this question, we're going to assume that the captured bears are a random sample. So then we get to our procedure. We have to list our hypotheses. So since we're testing for independence, the null is that transplant outcome and experience level are independent. The alternative is that they are not independent. Before we can do the test, we need to check our assumptions. So there's two assumptions. Do we have a random sample? And is it a large sample? If it's large, that means all expected counts must be greater than 5. You can't just tell me, yes, all expected counts are greater than 5. You have to show me. So first one, random sample. We're told to assume this in the problem. Literally the last sentence of the problem tells us this. So we're good there. Is it a large sample? Well, I calculated the expected counts and put them in my table in this pink color, or maybe magenta, whatever you want to call it. They're up here in this color. Are they all greater than 5? Yes. So we're good there. Since we're good there, we can proceed on to the test statistic. Notice I wrote the formula for it, and then I went on to the computation. You don't have to write them out like this. I chose to. That's just me. I'm a number freak. I want to see what impacts the chi-squared the most if I needed to see that. You can put the first two, ... the last one. That works. When all the dust clears, we get a chi-squared value of 0.0728. So then we take that and we look at our table. Well, first we've got to get degrees of freedom. So we do the number of rows minus 1 times the number of columns minus 1. So it'll be 3. There's 3 rows, so 3 minus 1 is 2. And there's 2 columns. So 2 minus 1 is 1. Which means we have 2 degrees of freedom. So if we take our p-value, we take our test statistic, and then we take our degrees of freedom, and we go and we look in our chi-squared table. We have 2 degrees of freedom. So we're going to look at this second row here. Chi-squared value is 0.0728. My smallest critical value is 2.77. So I'm going to be greater than 0.25, most definitely. So that's all I get from the table. If I type this in the calculator, and on this computer that I'm on, I can't show y'all, but it's second vars. And then you go down to option 8. The lower bound is the chi-squared statistic itself. So 0.0728. Upper bound is just a big number, and then your degrees of freedom. Put that in, you'll get a p-value of 0.9643. Our alpha, let's see, they didn't give us an alpha, but with a p-value that's 0.96, it doesn't matter what alpha we pick, we're going to fail to reject. There is not convincing evidence that transplant outcome and experience level are not independent. So there's not convincing evidence to say they're not independent, which means chances are they probably are independent. Okay, there's that one. Then we have this next one about squirrels and alarm calls and all that good stuff. And they ask us to test, is there convincing evidence that the responses to a single whistle is different for the different age groups? This is a test for homogeneity. I totally just misspelled that. Wow. Okay, anyways, this is a test for homogeneity. So we need to test at the 0.05 level of significance. The null is that the responses are the same for all 3 age groups. The alternative is that they're not the same. So is this a random sample? We're not told in the problem, so we must assume this. In order to do the test, we must assume this. Is it a large sample? Well, again, I put my expected counts up here in pink. So they're all greater than 5. That means we're good to go. Then we have our test statistic. Observed minus expected squared over expected. Again, you don't have to. I decided I'm going to write all these out. So I did. And calculated them individually and got a test statistic of 3.1466. To do the p-value, we need to get our degrees of freedom. There are 3 rows, so we do 3 minus 1, 2 columns, so 2 minus 1. That again gives us 2 degrees of freedom. So we need to get to that 2 degrees of freedom and see, where does 3.15 fit in? 3.15. Looks like we're in between 0.25 and 0.2. 3.15. Hopefully you can see my cursor here. That's kind of, well, if not, you can see where I highlighted. It's in between there. We fall closer to the 0.2, a lot closer to the 0.2, but we fall in between there. That's all we can get from the table. If we do it in the calculator, the p-value comes out to be 0.2074. So since our alpha is 0.05, our p-value is greater than that, which means we failed to reject H0. So there's insufficient evidence to conclude that the true proportion of responses are different for the different age groups. Okay, so let's kind of recap what we've had so far. We tested for homogeneity here. On number 4, we tested for independence. Notice how they're the same procedure. The only thing that really changes is your hypotheses. Same procedure. Only thing that changes are the hypotheses. And the last one. So we have some game managers wanting to look at hunting strategy for predators. In our case, it is mainly wolves. So in this park, they've got white-tailed deer, elk, and moose that they're looking at. And they're wanting to see how they were killed. There's in total, there are about 3,500 white-tailed deer, 1,000 elk, and 500 moose. So that means they have 5,000 total animals in that park, which we can take that, and since we're only looking at one set of data, really, this is a one-way table, which means we're looking to see if the true proportions match the proportions that are killed. Or this is also called a goodness of fit test. So if we let P1 be the true proportion of white-tailed deer, P2 of elk, and P3 of moose, we found the true proportion that's available, and we want to see if that matches what the wolves killed. So our null is the true proportions. P1 is 0.7, P2 is 0.2, P3 is 0.1. And the alternative is that H0 is not true. So we have to see, is this kind of random? Is it representative? We must assume the sample of wolves is representative of the population, because we're not watching the wolves, we're watching the prey. It says a radio-tagged wolves were observed to have killed prey according to the table below. Wolves were identified as the predators by their tracks in the snow. So we're going to have to hope that these are representative of the population of interest. And then is this a large sample? So are all the expected counts greater than 5? Well, again, I did that up here in pink, and I even labeled it this time, expected. They all are greater than 5. So just to recap how I got these, I did 166, which is the total killed, times the actual proportions. So times the 0.7, the 0.2, and 0.1. Okay, from there, we're able to move on and get our test statistic. Observed minus expected squared divided by expected. Again, I set them all up because I wanted to look at the values all individually. I mean, note that the moose total was way high. It was 8 point something. So that put our chi-squared at 15.3295, approximately. With the table, that tells us the p-value is less than 0.0005. We've got n minus 1 degrees of freedom, so 2 degrees of freedom. If we look for 15.32 along this row here, well, 15.2 is the highest it goes. We're above that, so we're smaller than 0.0005. If I do this in the calculator, I'll find the exact p-value is 0.000469. So yes, we are less than 0.0005. That's true. For our conclusion, since the p-value is less than alpha, remember our alpha was 0.05, we reject the null hypothesis. So there is sufficient evidence to conclude that the wolves are not selecting their prey at random. We don't know how they're selecting, we just know it's not random. Okay, so that's the review. For the hypothesis testing, we worked one of every kind. We did a one-way table. That's this one we just did. We looked at independence, which was number 4. And we looked at homogeneity, which is number 5. So we've done one of every kind of test that could appear on your test. So study it, study this review, know it, and good luck on your test.